Welcome back. The objectives of this video are to study concavity and inflection points. We'll take a look at the x and y intercepts of a function, and we'll do a couple of application problems. As mentioned in a previous video, an inflection point is where a curve changes direction. It changes from concave upward to concave downward, or vice versa. We'll need calculus to algebraically find where a curve goes from concave up to concave down, but visually we can see where that happens. So here's an example of a graph on the left that's concave up, and its inflection point is where we change directions here, probably somewhere between point 1 and point 2. And our rate of change is increasing, so we'll have a positive slope between a couple of points. This graph here on the right is concave down. The rate of change is increasing, and you can see here we go from an increasing rate of change to a decreasing rate of change. So concave up versus concave down. In example 4, we have a graph of g of x, and we want to find the intervals where we have the following behaviors. So our graph g of x, g is increasing. Make this a little smaller, we can see a little bit more here. G is increasing, and these, where it's increasing, again, we want to find the intervals, and those are the x values. So at what x values is our graph increasing? Where is it decreasing? Where is it concave up? Etc. So we'll go through this and answer these questions. G is increasing in the interval from -3 to 2, and it is increasing from 4 to infinity. So, and we can see that here, 4 to infinity and from -3 to 2. G is decreasing when x values go from -infinity to -3 to this inflection point at -3. And it is decreasing again. Looks like we have an inflection point here at 2 from 2 to 4. So using our interval notation, oh, that wasn't a very good infinity, from -infinity to -3 inclusive, and from 2 to 4. Where is G concave up? Well, it's concave up from -infinity to about -1/2. It looks like here, about this point here at -1/2, our graph goes from concave up, and now it starts moving concave down. So we'll say it's concave up from -infinity to -1/2. And then again, it's concave up from, looks like about here at 3 to positive infinity. And my guess is that's got to be a bracket there at 3. G is both increasing and concave up from -3 to -1/2, and 3 to infinity. And it is concave down from -1/2 to 3. And it's both decreasing and concave down from 2 to 3. I'm going to move this back to a parenthesis. So it looks like there's a little confusion here of when we might do brackets and parentheses. With increasing and decreasing functions, we use brackets, but at the concavity points, at the inflection points when we're discussing concavity, it looks like we're using parentheses. The next objective is to look at the x-intercepts and y-intercepts of a function. So the x-intercept is going to occur when y is equal to 0, or at points on the x-axis. Looks like we have some x-intercepts here at these particular points. So our x-intercepts, I'm going to write those as ordered pairs. So at -3, 0, 1, 0, and 4, 0. And on this particular graph, our y-intercept, where x equals 0 and its y value is -3, I'm going to write that as 0, -3. Now sometimes the x-intercepts, we might call those solutions, or we might refer to them as roots. And in that case, if they're solutions or roots, then we might just write them as the set -3, 1, and 4, and we don't worry about the ordered pairs. But I think as x-intercepts, I prefer that you refer to them in their ordered pairs. But when we talk about solutions or roots, we can just write those particular values. In sample 6, we want to find the x-intercepts for the given function algebraically. So we have 4 terms here. We want to find out where we want to find both the x and y-intercepts. The y-intercept is going to be easy. That is going to be f of 0. When we put 0 in, well, all those terms drop out, and that's 12. So our y-intercept, we can really eyeball that, and that's just going to be at 0, 12, or the constant of our function. The x-intercept, now this guy we're going to have to factor. I'm going to factor by grouping, and we'll take a look at this, and we'll do plus a minus here, and we'll go ahead and factor by grouping. So our x-intercepts, I'm going to factor out the greatest common factor in each pair. So I factor out the x squared, and I'm left with x minus 3. And again, I'm going to factor out, in this one, I'm going to factor out -4. And I'm left with x minus 3. So good news is my left behind here is the same thing. My 2 factors now are x squared minus 4 times x minus 3. We set this equal to 0 because we want our y value to be 0. And then we can continue to factor x squared minus 4. That's a difference of 2 squares. So x plus 2 times x minus 2 times x minus 3 is all equal to 0. And then we can solve for our x values, and x equals plus or minus 2 and x equals 3. So those would be our zeros, or our roots, our solutions, and our x-intercepts. We could probably write that plus or minus 2, 0, and 3, 0. So those would be our x-intercepts. I promised a couple application problems. Here we have a problem in which we have Tina's a sales clerk. She earns $325 base pay plus $18 for each item sold. We want to express her salary as a function of the number of items sold. So our function name is G. The number of items sold is X. She's getting $18 for each item sold, so that's 18x. So our function is G of x equals 18x. $18 times each item sold, plus she gets a base salary of just $325. So if she sells nothing, she gets $325. Find her gross pay if she sells 24 items. We're going to put 24 in for x, and we go 18 times 24 plus 325. We might need our calculator for 18 times 24. That's 432 plus 325, and G of 24 then. She sells 24 items, she will earn $757. Sample 8, we give you the formula here, h of t. If you drop your book from a height of 45 feet on the planet Newton, its height in feet after t seconds is identified by this function. How long does it take for the book to hit the surface of the planet? The surface would be the ground, and that would be a height equal to 0. Not our time. H of t, our height, is with respect to time, so h of t is 0. So now our input is not 0, but our output is 0. We would say 0 equals 45 minus 14t squared, and then we want to solve for t. So add 14t squared to both sides, it equals 45. Divide by 14, and we get t squared equals 45 over 14. Square root both sides, and t is equal to, we could do plus or minus here, but having negative time doesn't make sense, so we're just going to use the positive. Square root of 45 over the square root of 14. We put that in our calculator, and we get t equals 1.793 seconds. And we'll get some more practice with this when I see you in class.